This is the second part of our video on stoichiometry, and here we're going to talk about reaction stoichiometry. Okay, so when you balance an equation, the balancing coefficients tell us the mole ratios between products and reactants. For example, let's look at the combustion of octane. We balanced this equation. This was one of the first that we balanced. 2 octanes react with 25 oxygens to produce 16 carbon dioxides and 18 waters. So, one more time, these numbers and the balancing coefficients, these tell us mole ratios. Mole ratios, right? So what we're saying is that 1 mole of octane produces 9 moles of water, right? That's 2 to 18, which simplifies down to 1 to 9, okay? Or 1 mole of octane produces 8 moles of CO2. 2 to 16 is the same as 1 to 8. Or we could say that 9 moles of water are produced for every 8 moles of carbon dioxide. Or we could say 25 moles of oxygen are consumed for every 2 moles of octane. So let's continue using this as an example. Let's ask a couple of questions here. So for example, how many moles of oxygen would be consumed by the combustion of 0.25 moles of octane, right? So we take the 0.25 moles of octane and we multiply it by the mole ratio. 25 moles of oxygen per 2 moles of octane says that 6.25 moles of oxygen would be consumed. Or we could do the same thing for the carbon dioxide. How many moles of carbon dioxide would be produced by the combustion of 0.25 moles of octane? So we take 0.25 moles of octane times the mole ratio, 16 to 2, is basically 4 moles of carbon dioxide. But that's not really where we want to go with this. That's just an intermediate step. And this is where we want to go with this, is we can carry this one step further. And then we can use the balanced chemical equation to calculate gram ratios. So we want to convert, we balance the equation, and then we want to convert the balancing coefficients, basically, which is the mole ratios, into gram ratios. In other words, we want to be able to ask a question like, if you start with so many grams of octane, how many grams of CO2 would you make, and how many grams of water would you make? Okay, so this is a 3-step process after you balance the equation. You divide the number of grams by its molar mass, right? This converts grams into moles, right? Dividing mass by molar mass gives you moles, right? So we're going to go grams to moles. Then we're going to apply the reaction stoichiometry like we just did in the last example, okay? And then we're going to convert the moles back into mass again. In other words, we want to multiply by the molar mass of the substance sought. Okay, which is not as bad as it sounds. Let's work through a couple of examples. So let's continue working with our octane reaction. And let's say, all right, so how many grams of oxygen are required to react with 100 grams of octane? Right, so we'll follow this 3-step process. So the first thing we have to do is convert that 100 grams into moles. We want to convert grams into moles, right? So we have to do that. We have to have the molar mass of octane. So octane is 8 carbons and 18 hydrogens. So 8 times 12.011 plus 18 times 1.0079 comes out to be 114.23 grams per mole. Okay, So let's see, do we have more than or less than a mole? It takes 114.23 grams to make a mole. We only have 100 grams, so we don't quite have a mole. So we divide 100 by 114.23, and you get 0.875 moles. Okay. Then we're going to apply the reaction stoichiometry. Okay, we're going to apply the reaction stoichiometry. So we have 0.87 moles times the mole ratio between oxygen and octane. You have to go back to the balanced equation to get that, but it was 25/2. That's 10.93 moles of oxygen. Okay. And last, we can convert moles back into grams again. Okay, so we take the 10.93 times the molar mass of oxygen is 32, is 350 grams of O2. Now, you might wonder where I got 32 from. Oxygen has a molecular weight of 16, but remember we were dealing with O2 molecules. 16 is the weight of an individual oxygen atom, but oxygen occurs as O2 molecules. And 32 is the mass, 32 grams per mole is the mass of an O2 molecule. So that's 350 grams of oxygen. So basically your 100 grams of octane produces 300, or not produces rather, but requires or consumes 350 grams of oxygen. Okay? Now let's do the same calculation for the carbon dioxide and then the same calculation for the water. So the first step we've already done. The first step we already did. We convert grams into moles. So if we start with 100 grams of octane, we calculated the molar mass of octane, you divide, that comes out to be 0.875 moles. Okay. Then we apply the reaction stoichiometry. And the stoichiometry between the octane and the carbon dioxide is 1:8. So you take 0.875 moles of octane times 8 moles of carbon dioxide per mole of octane, says that 7 moles of carbon dioxide are produced. Okay. And so now we convert moles back into grams again. So what's the mass of 7 moles of carbon dioxide? You multiply by the molar mass of carbon dioxide, which comes out to be 44 grams per mole. And this comes out to be 308 grams of carbon dioxide. Right? So your 100 grams of octane, when you burn it, produces 308 grams of carbon dioxide. And then last, let's do this calculation for the water. Okay, so how many grams of water are we going to produce? First step, grams into moles. This is the same first step through all 3 calculations. So we already did this twice now. Your 100 grams of octane is 0.875 moles. Then you apply the reaction stoichiometry. Basically, it's 1:9, so you're multiplying by 9, or 9 moles of water for every mole of octane produced. That comes out to be 7.87 moles, right? And then our last step is we go moles to grams. You know how to do that. Multiply by the molar mass. At 7.87 times 18 grams per mole is 142 grams of water produced. So let's look at this equation. Let's tile this together. So octane, 2 octanes, when we balance this equation, 2 octanes, 25 oxygens make 16 waters and 16 CO2s and 18 waters. So these are all the calculations that we just did. if we started with 100 grams of octane, we consume 350 grams of oxygen. We produce 308 grams of CO2, and we make 142 grams of oxygen. Now I want you to note something important here. We add up 100 and 350, what do we get? 450. So you had 450 grams of reactants. Okay? If we add up 308 and 142, what do we get? 308 plus 142 is 450. So we start with 450 grams and we finish with 450 grams. And this serves to illustrate an important point that like we said, that matter is conserved in a chemical reaction. You have the same number of atoms and the same number and same type of atoms when you finished than what you started with. All we did was all chemical reactions do is rearrange the atoms that are already present. That's all we're doing. So here the carbon is tied up with the octane, and here it's tied up with the CO2. And here the hydrogen is tied up with the octane, and here it's tied up with oxygen. But we have the same number of atoms on both sides of the equation. All the chemical reaction does is rearrange the atoms that are already present. All right. So there's still a few things that we need to talk about here. And the next is this concept of limiting reactants. Okay, you might not have enough of one reactant to completely react with another. Okay, and the quantity of product that can form is therefore limited. That's why we call it a limiting reactant. Okay, so for example, formation of zinc sulfide. Okay, so suppose I ask you this question. How many grams of zinc sulfide can be produced by 100 grams of zinc and 100 grams of sulfur? And before you jump to the conclusion that the answer is 200, it's not. Okay, now while the mass will be conserved, and if we start with 100 grams of product, or reactant rather, we'll finish with 100 grams of product, but that doesn't necessarily mean we're going to make 200 grams of zinc sulfide. We'll have 200 grams when we finish, when the reaction is done, but that doesn't mean it's all going to be converted over to zinc sulfide, right? Because these two elements don't have the same mass. We might be starting with 100 grams of each one, but 100 grams of zinc is not the same number of moles as 100 grams of sulfur. So what we have to do is we have to figure out which one of these is present in smaller quantity. In other words, convert the 100 grams into moles and then see which number is smaller, and that tells you how much product you can produce. So here's just the question restated, so I got it all in one page. If you have 100 grams of zinc and 100 grams of sulfur, how many grams of zinc sulfide can you produce? So we have to convert each of these into a number of moles, right? So you guys know how to do that. We're going to convert grams into moles. You divide by the molar mass. So you find zinc on the periodic table. It's a transition element, the last transition element, and the 65.4 grams per mole. So we take 100 grams divided by 65.4 grams per mole, tells us that we have 1.53 moles of zinc. Okay, how many moles of sulfur do we have? 100 grams of sulfur divided by the molar mass of sulfur is 3.11 moles of sulfur, right? So we really only have about half as much zinc as we do sulfur because the zinc is heavier. The zinc is almost twice the weight, a little more than twice the weight. So we have 3.11 moles of sulfur, but only 1.53 moles of zinc. And so we therefore call zinc the limiting reactant. So how much zinc sulfide can we form? only 3.1, or excuse me, only 1.53 moles. So how many grams is that? Okay. So what's our molar mass of zinc sulfide? 65.4 plus 32.1 is 97.5 grams per mole, right? And then we multiply that by 1.53 moles, and you get 149 grams. So that's how much zinc sulfide you can produce. And you may be thinking, well, wait a minute, you just said mass is conserved. And it's true, mass is conserved. If we start with 100 grams, 200 grams total, we're going to finish with 200 grams. So where's the other 51 grams? Where did the other 51 grams go? It's going to be in the form of unreacted sulfur. We'll react all the zinc. See, we have more zinc than we do sulfur. I'm sorry, other way around. We have more sulfur than we do zinc. So we'll react all the zinc, and there'll be sulfur left over. And that is the next part of this problem, is how many grams of sulfur remain after the reaction is complete. There's two ways to work this problem. So probably the easiest way is the way I just did it. You can practically do it in your head. Okay. Since there's 200 grams before the reaction, there has to be 200 grams after the reaction. And because the sulfur was present in the fewer number of moles, the mass that's unaccounted for, the 51 grams that's unaccounted for, must be in the form of unreacted sulfur. Right, so we take the 200 grams that we started with, minus the 149 grams of zinc sulfide that were produced, gives us 51 grams of unreacted sulfur. The other way we could get at this information, this was probably the easier way, this way is probably a little harder. Here we're doing it from grams. We could also do it from moles. Okay, so if there were 3.11 moles of sulfur, but only 1.53 moles of zinc, how many moles of sulfur will be left over? 3.11 minus 1.53 tells us that there's 1.58 moles of sulfur remaining. So what's the mass of 1.58 moles of sulfur? 1.58 times 32.1 is 51 grams, which is basically the same answer. So here we did it with grams, and here we did it with moles, but in a way we were doing the same thing. You have the total mass. Total mass is the same before and after the reaction. So let's throw another monkey wrench in the machinery. Okay, we're almost through. So what if the reaction stoichiometry is not 1-to-1? Okay, what if the reaction stoichiometry is not the 1-to-1? So what if we're talking about the reaction of sodium and sulfur to make sodium sulfide? Okay, so suppose I ask you this question. If 100 grams of sodium are reacted with 100 grams of sulfur, how many grams of sodium sulfide could be produced? Okay, now, like I say, now it's not 1-to-1, right? Because you have to have 2 sodiums for every 1 sulfur. So we have to take that into account when we figure out our limiting reactants. So let's first divide each by the mass, molar mass, and convert it into moles, right? So 100 grams divided by 22.9 grams per mole. I multiplied by the reciprocal instead of dividing, which is the same thing. 100 divided by 22.9 is 4.36 moles of sodium. Okay, and 100 grams of the sulfur divided by the molar mass of sulfur, which is 32.1, is 3.11 moles of sulfur. So you might be real quick to jump on here and say, oh, well, sulfur is the limiting reagent, but it's not. because you have to have 2 moles of sodium to make the mole of the compound, whereas you only have to have 1 mole of sulfur. So the sulfur is not the limiting reagent. What you have to do is, before you can jump to any conclusions then, is you divide each by its coefficient in the formula. So there's 2 sodiums required for every 1 sulfur. So we take the 4.36 moles of sodium, divide that by 2, and you get 2.18. And 3.11 divided by 1 obviously is 3.11. And then you look at which of these numbers is smaller. That tells you what the limiting reagent is. And the limiting reagent is actually sodium. So now we work the problem like we did the last. So basically then, what's the mass of 2.18 moles of sodium sulfide? We figure out the molecular weight of sodium sulfide, 2 times 22.9 plus 32.1 is 77.9 grams. Okay, grams per mole rather. And we multiply that by 2.18 moles. Okay, and you find out that we can make 169.8 grams of sodium sulfide, right? So one more time, you take each mass and divide it by the molecular weight to figure out the number of moles, but then you also have to divide by the coefficient in the formula. So let's work one more example like this, and this is our last slide. Okay, so let's work one just like this except for aluminum sulfide. And now while we have coefficients associated with both in the formula, both of the elements have coefficients. Alright, so if I ask you this question, if 100 grams of aluminum are reacted with 100 grams of sulfur, how many grams of aluminum sulfide can be produced? Alright, so if you remember how to write formulas, aluminum is a +3, sulfide is a 2-, so our formula is Al2S3. So when we write the balanced equation, we have to put a 2 in front of the aluminum and a 3 in front of the sulfur. Okay, so 2 aluminums and 3 sulfurs make 1 aluminum sulfide. So we take our 100 grams of aluminum, divide that by the molar mass of aluminum, that's 27 grams per mole, and that's 3.70 moles. Okay, but then you divide that by the coefficient in the formula, which is 2. So really it's only 1.85 moles of aluminum sulfide that we could make. And then we do the same thing for the sulfur. You divide the 100 grams by the molar mass of sulfur, that's 3.11 moles, but then you have to divide that by the balancing coefficient in the formula, that's 3.11 over 3, that's 1.014. So now you see that the sulfur is the limiting reagent. Only 1.04 moles of aluminum sulfide can form. Okay, so you know where to go from here, correct? We have to figure out, okay, so what's the mass of 1.04 moles of aluminum sulfide? We have to first figure out the molar mass of aluminum sulfide, right? So that's 2 times 27 and plus 3 times 32.1, and that comes out to be 150.3 grams per mole. Okay, and we multiply that by 1.04 moles, and you get 156.3 grams. Okay, and that is the End of this video.